Okay, today in class we have done our homework call and we've done the background of writing these different reaction types. And we wrote those down out of the book as our do now. And we did everything but ox-red and acid-base. So what we're going to do right now is we're going to kind of fill in the blanks. So those of you at home, you should leave about 1 or 2 spaces between each of these as you copy them down. So our first reaction type is synthesis, and I'd like you to turn to page 284 of your textbook. And I'm going to finish off this video and make a second video of the actual application of these rules, but this will just be the rules one. So as you're looking at page 284, you'll see synthesis, and you'll see synthesis is being done with sodium and chlorine. And this reaction, by the way, is very, very hot. If you look in the middle of that page, you'll see 2 sodium atoms and 2 chlorine atoms that are put together as molecules because that's the way chlorine goes around in nature. And chlorine and everybody in group 17 are going to be doing exactly the same thing. But this reaction is exceptionally hot. I mean, it will blind you if you look at it. It's that hot. So what's going on? We have 2 individual elements, A and B. In the book, it's sodium and chlorine that are forming a third compound, and in this case, it's the ubiquitous, known by everyone, everybody's put it on their food, sodium chloride. Okay? This is a synthesis reaction. All right? Next, we have a combustion reaction. Would you please write down the sodium-chlorine reaction, okay, from the textbook? It has 2 sodiums plus 1 chlorine molecule are giving you 2 sodium chloride molecules. And we'll talk about how that goes when we do the reactions. Combustion is our second one. Now, combustion requires oxygen on the left side of the equation. Would you make a note underneath your combustion one when you put this down that this requires oxygen as O2? The carbonate ion has 3 oxygen atoms combined with 1 carbon. If you see that on the left side, that will not be the signal to you that that is a combustion reaction. It has to be oxygen as O2. Yeah, there we go. Got that together. Next is the decomposition. Decomposition is 1 becomes 2. One substance, that is, becomes 2. Oh, stop there. All right. So A and B are together at the beginning, and then they are separated into A and B as part of the reaction. Single replacement. Oh, and let's look at the what you have in the textbook. Let's start with combustion. Combustion is on page 285. And why did you use the copper oxygen or the carbon oxygen? 1 carbon atom and 2 oxygen atoms together as the oxygen molecule will form carbon dioxide. It's a nice, simple combustion reaction. Now let's look at the one right below that, where methane and oxygen combine to form carbon dioxide and water. In that one, you're seeing exactly the same thing going on, except we started with methane instead of just a carbon atom. So notice oxygen is on the left, and you see the CO2 on the right? That O2 is not what you're looking for on the left side. Okay, if CO2 were on the left and oxygen were on the right, this would not be combustion. The oxygen has to be on the left side of the equation, or you don't have combustion. Okay? And combustion always produces heat. The forest fires that we've had, the wildfires up in our hills and up in Santa Barbara area and Ventura County in general. All of that stuff was combustion. And guess what? Firefighters know if they can get rid of oxygen, they can stop the fire. The other way to stop the fire is to get rid of A. In this case, it's trees and branches and brush that's dried out. Okay? So either one will stop the reaction. So oxygen, have you ever heard of or heard on the news, they have the foam dropping helicopters over the fire now, and they're dropping foam everywhere. What does that foam do? What do you think? It's like putting a blanket on it and making it impossible for oxygen to get to the fire. It's very, very effective. Very effective. Okay, so we did combustion, decomposition. One substance is becoming two. It breaks into two pieces. Single replacement. That's a hot reaction. When I finally get around to doing that thermite reaction that I've been promising you for the last 3 weeks, you're going to see a really hot reaction, because single replacement is really, really hot. Okay? So, anyway, single replacement. In the case of thermite, it's going to be rust, and the C is going to be aluminum. And aluminum is going to replace the iron, single replacement, to form iron oxide, and the iron, to form aluminum oxide, and then the iron, because the reaction is so hot, will be melted. It will literally flow like liquid. And if you put your hand under it to catch that liquid, it will go right through your hand. But it's okay because you won't bleed. It'll be cauterized. I like to give graphic explanations. Anyway, double replacement. That's where we're switching partners and dancing. Okay, this is what we did in that lab. Okay, that beautiful lab where we had the acetate and all the things that we reacted together, 72 reactions. And they had all kinds of different colors and whatnot. All of those except the carbonate one with calcium carbonate and hydrochloric acid. Remember, that was the one that made bubbles? Okay, that is not a double replacement reaction. Okay? Double replacement reaction. Would you write down below this that charges will not change? And you'll see why it's significant later. But right under double replacement, that charges on ions will not change. Oxred. This guy is right here. Charges on ions do change. And for that reason, this is a second way of classifying those first reactions. This will always be an oxred. Oxred is the second way to classify any synthesis reaction. Combustion is also oxred all of the time. Decomposition, oxred sometimes. Not always. So you got to be careful with this one. And single replacement is oxred, but double replacement is not. There we go. Now, acid base. I've given you background on that down here. If you're watching this at home, you want to write all this stuff down to help you understand acids and bases. I'm not going to show this very long in class nor on the video. So it's available on my website on week 5, in week 5 on today, which is Wednesday, you can see all of this stuff. And here is what happens in an acid-base reaction. How many of you have had experience with acid-base reactions before? No? Guess what? You've all had experience with acid-base reactions. Any of you ever used vinegar on a salad? Vinegar is an acid. Yeah. And yes, there will be acid-base reactions going on there. And let's see, how we done on time? All right, here's a few examples before I do the homework. This guy is your very first one, synthesis. Okay, this one right here. So synthesis, what did I tell you? Synthesis is always going to be in addition to synthesis. Did you write it down? Oxred. Yeah. See, synthesis, combustion, decomposition sometimes, and single replacement. Okay? These three, synthesis, combustion, and single replacement, will always be oxred. And the way you'll know that it's oxred is you're going to have an element on one or both sides. So synthesis is also oxred. And let's see why. What's the charge on iron, the element? No, that's iron, the ion. What's the charge on iron, the element? You're thinking valence electrons. It's not valence electrons. No, everybody on the periodic table has the same charge. Everybody on the periodic table has the same charge. Everybody. Okay, let's take one example. Let's do fluorine. Our non-metal, screaming Mimi, electron-grabbing fluorine. Okay, fluorine. How many protons?
9.
9. How many electrons?
9.
What do you have when you have 9 protons and 9 electrons? What's the charge? What's the charge? Come on.
1.
You have 9 positive protons. You have 9 electrons. Before it forms an ion, it's always going to start out as 9 and 9. It's neutral. Everything on the periodic table is neutral. They all have the same number of protons and electrons. Okay? I know once we start doing ions, you always think of them as ions, but that's only when they've lost or gained electrons. Okay? So what's the charge on iron on the left side here? 0. What's the charge on chlorine? 0. What's the charge on iron on the right? Did the charge change? Yes. Oxred. Oxidation reduction is signaled by a change of the charge of the element from left and the right sides. If they're different, it's oxred. And that's why they're always so hot. There's a lot of energy gets released when elements become ions or ions become elements. Always hot stuff. Oxred's always hot. Okay, what's the second one? What is this guy? I just put the arrow there. Yeah, but what's the reaction type? Yeah, combustion. Now, why is it combustion? O2, but where is it? O2 is on the left. That makes it combustion. And all combustion reactions are oxred. Yeah, A is hydrogen in this case.
Yeah, but
The order of the elements does not matter. It's just that you have oxygen, O2, on the left side of the equation, not as the first reactant necessarily, because the order in which you write your reactants doesn't matter. Okay? So, over here, on the left, oxygen has no charge. How about hydrogen? Hydrogen has 0. Now, when it's together with oxygen, what's happened? Hydrogen goes partially plus, oxygen goes partially negative. That makes oxidation reduction. Oxide, change in charge. Okay? So all combustion is change in charge. All right, what do we have in this next one? KClO3 produces oxygen. Come on, what is that signal? Change in charge. Starts with an O. Oxide. Okay, is this combustion also?
no.
Why? It has O2.
The O2 is on that.
Okay, that's the reason. O2 is on the right. O2 has to be on the left for it to be combustion. Okay, so what else do we have? What do we have when 1 becomes 2? Decomposition. Right, this is a deck. Decomposition. Okay, what do we have on the last one? Lithium and water giving lithium hydroxide and hydrogen. Do we have an element on either side? What element do we have on the left? It's all alone. What is it? Lithium. Good. What do we have as an element on the right? It's all alone. Hydrogen. Hydrogen. Hydrogen and hydrogen. That's the way hydrogen travels around in nature. Okay? So we know that this is what? Charges have changed. Oxide. And what else is it? Single replacement. Excellent. How about that, huh? Now as we start doing your worksheet, you're going to see this even more graphically get a little bit easier and easier for you. And that's it for this one. Next we're going to do some of your homework, and that will be on a separate video.